Hello, in this video we're going to talk about the first part of Chapter 2. Do note that we're going to skip Section 2.3, the separation of mixtures. Since this content is familiar to many of you, I'm going to go through parts of it quite fast. And if it's not as familiar to you, that's totally okay. Just read the book and come chat with me if you have questions, and we'll all get on the same page. Okay, so we have millions of chemicals on the planet. They're all made from 118 elements. Elements are a substance that cannot be broken down into simpler substances. Each unit of this simple substance is called an atom. On the other hand, a compound consists of two or more elements. We abbreviate the elements with these chemical symbols, where we have one or a two-letter abbreviation. The first letter is always capitalized, the second letter is always lowercase. In this case, the HE is the abbreviation for helium. Here's a list here of common metals and their elemental symbols. Often the elemental abbreviation is related to the English word, but not always. Sometimes it's related to the Latin word, in which case it won't make a bunch of sense to us native English speakers. And here's an example of the elements whose symbol corresponds to the Latin name. Okay, elements can be divided into three classes. The metals are typically solid. They make good wires or pans or things like that. Nonmetals vary greatly. You can have gases, solids, but typically they don't conduct electricity. And then metalloids are kind of in the middle. Now, if you know about this magical thing called the periodic table, which our book hasn't quite explained to you yet, there you go, there's my little periodic table. The metals are typically here, in this area, metals. The nonmetals are typically over here, nonmetals. And then the metalloids are kind of in the middle. Metalloids, sure. But we'll get to that later in Chapter 3 when we talk about the periodic table more specifically. Now, some elements exist naturally as diatomic molecules, in that oxygen's a great example of this. Every oxygen atom you find hanging out naturally in the air consists of a pair of two oxygen atoms bound together. And many of the gases do this. Iodine's a solid, but the rest of these are gases. And this is just something you should know. Which one of these form diatomic molecules? I usually don't test people on this specifically, but it comes in handy later when you're trying to make chemical equations for, say, something burning in air, and you need to know that the oxygen's present as O2. There's an abbreviation or a mnemonic for this you can use. Have no fear of ice-cold beer, if you would like. Again, if you're familiar with the periodic table, on the periodic table, the elements that are present as diatomic include hydrogen over here, and then kind of an L shape over here from nitrogen, oxygen, fluorine, chlorine, bromine, iodine, down that way. So you can think of it that way as well. Another way to think of it is that only diatomic elements end with the suffix -ine or -gen. Something we should also mention is that many elements exist in different allotropes. These are different forms of an element. For example, oxygen exists as O2 or O3, which we call ozone. Carbon exists as either diamond or graphite, or carbon nanotubes or buckyballs or other unique forms of carbon. Some elements can consist of 4 or 5 different allotropes. It's a wide variation there. But just do keep in mind that this is a possibility. I won't specifically expect you to know this, I just want to point it out while we're talking about elements. Okay, you're most likely familiar with the fact that we commonly discuss 3 states of matter. These are the most common ones. There's, in addition to solid, liquid, and gas, you can have plasmas or supercritical fluids, but we're not going to get there in this course. So generally you have a solid, a liquid, and a gas. Feel free to read the descriptions here. Usually it's helpful to include the state with the formula, whether it's a solid, a liquid, or a gas. That just depends on what you're trying to do. Sometimes that's important to include, sometimes it's not. When in doubt, you can just throw it in there and you'll be safe. Here's a picture from your textbook, again, describing a solid, a liquid, and a gas. Feel free to pause the video and take a look if you'd like. Next on our list to talk about is the law of constant composition and how this gets us towards our knowledge of atomic theory. So there's a rich history behind the discovery and acceptance of atomic theory. Shouldn't really say discovery because this has been philosophized since the ancient times, but the actual proof and getting all of science on board with atomic theory didn't happen until the mid-1800s. And on our way there, conceptually, we can think first about the law of constant composition, which is that the relative amount of each element in a particular compound is always the same, and this is a good excuse for us to introduce mass percentages. So a mass percentage is a fairly simple concept. You have the mass of one element divided by the total mass of the compound times 100. It's just like every other percentage. So for example, water, you could say the mass of hydrogen can be written this way, the mass percent of hydrogen can be written this way. The mass percent of oxygen can be written this way. And now if someone told you that they had a 12.302 gram sample of water, and they said it had 1.368 grams of hydrogen and 10.934 grams of oxygen, you can calculate what the mass percentage of each are. This is kind of a contrived example because no one's going to give you numbers like this, but it allows us to illustrate our point. So here's the mass percent of hydrogen, mass of hydrogen over the total sample of water. Here's our mass of oxygen, again the mass of oxygen over the total mass, and you get these numbers after you multiply by 100. So the law of constant composition, back to that, it says that the mass percentage of hydrogen in water is always going to be 11%, 11.12%. The mass percentage of oxygen is always going to be 88.88%, regardless of where the water comes from, what you do to it, etc., etc. As long as it's still water, this is true. So this conceptually, and the law of multiple proportions, which I paraphrased it down on the bottom of this slide, that basically says atoms combine together to form compounds in simple whole numbered ratios. These ideas together led us to our modern understanding of atomic theory. It's credited after Dalton. Okay, so in atomic theory, matter is composed of small indivisible atoms. This indivisible part's not necessarily true. We now know that we can split atoms in nuclear fission processes, but that's kind of the next level that we don't need to worry about at the moment. The second concept in atomic theory is that all atoms of a given element are identical in mass and chemical behavior. This is also not quite true because different isotopes have different mass. We'll get to that later in this chapter. And then different allotropes have different chemical behavior. So it's not quite true, but it's a good starting point here. Okay, atoms of different elements do definitely differ in mass and behavior. Compounds are composed of atoms put together in different integer ratios into something called a molecule. The amount and ratio of different elements defines the molecule. The fact that you have 2 hydrogens and 1 oxygen in this molecule is what makes it water. And in a chemical reaction, the atoms are rearranged and reconnected, but the atoms themselves are not created nor destroyed. So something we can do with atomic theory is we can set up a scale of relative atomic masses. So say we know water contains 2 hydrogen atoms and 1 oxygen atom. So if we look at the mass percent of oxygen and the mass percent of hydrogen, and say we're going to use hydrogen as our reference point. Hydrogen is 1, whatever we're talking about. In this case, it's going to be atomic mass. The mass of an oxygen atom, if you look at the mass percentage here and divide it by the mass percent of hydrogen, and then you have to divide the mass percent of hydrogen by 2 because there's 2 hydrogens per water. Okay, if you do the math like this, you get 15.99, which says that the mass of an oxygen atom is about 16 times heavier than the mass of a hydrogen atom. So this way we can set up a scale of relative atomic masses. The example I just used uses hydrogen as a reference. In reality, a form of carbon is used, carbon-12, when we talk about isotopes. And so therefore, when you look at the periodic table, the atomic mass of hydrogen is not exactly 1, because the scale is set up relative to carbon-12. These atomic mass ratios are used throughout science. They're what you see in the periodic table. It's how we describe the mass of elements. So, atomic mass. One atomic mass unit is exactly 1/12 the mass of a form of carbon, carbon-12. We haven't talked about what carbon-12 is different than carbon-13, etc. That'll come later when we talk about isotopes. Atomic masses are unitless. They are a ratio to other atoms. We can give them a unit because that makes us feel good about ourselves. We call it the atomic mass unit, U. Or we might call it AMU, atomic mass units, although that's a somewhat older definition. In biochemistry, they tend to use Dalton, in honor of the Dalton who's credited with atomic theory. They'll also use kilodalton in biochemistry, because often they're dealing with things that are bigger than 1,000 daltons. So you can phrase the atomic mass of hydrogen in a number of different ways. Okay, so we said that one atomic mass unit is 1/12 the mass of carbon-12. But if you look on the periodic table, carbon doesn't say 12, it says 12.01. And this is because carbon exists as a mixture of isotopes. The number you see in the periodic table is a weighted average. It's the mass of each isotope multiplied by its natural abundance, how prevalent it is on Earth. And then you add to that the mass of the next isotope multiplied by its natural abundance, so on and so forth, and you get the number in the periodic table. But again, that's something we'll get to later in the chapter. I just want to put it here for completeness in case you already know that, so you know how this all fits into your existing knowledge. Okay, we talked about atoms, and then we said atoms combine together to form molecules. So let's define a molecule. It's at least two atoms in a definite arrangement. The connectivity matters, and only nonmetals and metalloids will actually function as molecules. The metals, for various chemical reasons, don't come together in this fashion to form molecules. So we'll write these molecules kind of laid out in various structures like this, with lines to indicate bonds between the two atoms. These are covalent bonds, and we'll get into exactly how bonding works in Chapter 7. Okay, other ways that you see molecules depicted, you'll see it either with the formula on the top line or as the structure, which we just showed. You'll also see them with ball and stick models, where each atom is a sphere and they're connected by sticks. That one's not so realistic, but it matches what we can do with model kits, so we still include it, and it's a little easier to see. Probably the most physically correct version is the space-filling model down here. And this is more what it would actually look like if you could see it and it was a solid shape. Atoms are not solid shapes. They're squishy and defined by electron clouds, and that's something we'll get to later too. But hey, we got to draw them as shapes so we can see them, and so we tend to make them nice solid shapes. Okay, so we said this before. Chemical reactions are the breaking and forming of chemical bonds. So if you take hydrogen and oxygen, put it together, light it up, it makes a nice explosion, and you get water vapor out of it. And so in the process of that explosion, the bonds between the hydrogen atoms break, the bonds between the oxygen atoms break, and then they form together as water. And this is what happens during a chemical reaction. Now, something else we need to talk about while we're here is molecular mass. So the molecular mass is the sum of the atomic masses of all atoms in the molecule. This seems a little pointless to do now, but when we start talking about grams per mole and stoichiometry in the next class, this is going to become very important. So let's introduce the concept here. So if you want to know the mass of the molecule, you simply just add up the mass of all the atoms involved in that molecule. So say you have carbon dioxide, your mass of the whole molecule is just the atomic mass of carbon, because there's only one carbon, and then 2 times the atomic mass of oxygen, because there's 2 oxygen atoms in this molecule. Something that I kind of left assumed, which is probably not fair of me to do, is when we write CO2, subscript 2, it means that there's 1 carbon and 2 oxygen atoms. This is different than if we were to write 2 CO2, which would mean that you have 2 complete carbon dioxide molecules. Okay, so some foreshadowing is the molecular mass is numerically equal to the molar mass of the compound. And we set this up on perfect by defining the mole so that this is true, is you can take this number in atomic mass units and then just change the units on it to say this many grams are in 1 mole of the molecule. And then it makes our whole number system consistent and work really well. And so we'll talk about what grams per mole and what the heck a mole is. We'll talk about that later. So an example, to calculate the molecular mass of caffeine, here's the formula of how many atoms of each type are in caffeine. If you want to calculate this, you could just do the math like this. You can pull off of whatever source you have. The periodic table is a perfect source for this. You pull off the atomic mass of each one, of each atom. For carbon, you'd have 8 carbon atoms times the mass of carbon. For the hydrogen, you'll have 10 hydrogen atoms times the mass of hydrogen. For nitrogen, you'll have 4 times the mass of nitrogen. And then for oxygen, you have 2 times the mass of oxygen. And then you add this all up, and you get your answer. And if you're going to be picky about sig figs, here's how your sig figs come out. Generally, when you're working with atomic masses and molecular masses and molar masses, you should just take as many sig figs as you can and use it. This is an experimental number, it's not exact, so it can limit your sig figs in your calculation, but it's always a good goal to try to have this number not be the limiter of your sig figs. Okay, so now we can get back to mass percentages in a much more useful format. So, a little earlier we defined mass percentages, the mass of one element over the total mass of the compound, and we just gave you masses of each and you calculated it. But now that you know how to calculate molecular masses on your own, you can find this mass percent a lot more easily. So this is also called percent composition by mass. It's the percent by mass of each element in a compound. The reason why this is important is because experimentally we can determine the percent composition by mass, and so then you can use that plus your theoretical calculation of, for this given formula, what the percent composition of each element should be. You can use the experimental and the theoretical values and compare them and see if you made the compound that you think you made, something that's done relatively often in chemistry. This is also helpful if you're trying to calculate how much nitrogen you deliver by giving so much ammonia. You can figure out the mass of nitrogen that's delivered from the mass of ammonia. So it's the same formula, but now you can plug in numbers a little more readily. Well, rephrase the question. What percent of the weight of ammonia is due to the hydrogen atoms? Okay, the atomic mass of hydrogen is here, the molecular mass of ammonia is here, and you put it together into the formula, multiply by 100, and you'll get your answer. So 17.7553% of the mass of ammonia is due to the hydrogen atoms. The rest of that mass is going to be due to the nitrogen, since it's the only other component in the molecule. Okay, and that's what we have for now. Thank you for your attention.